Good afternoon, or good evening, or good morning. My name is Howard Stone, and I would like to welcome you to the 2020 Holiday Science Lecture with the title, A Materials Wonderland, a celebration of how material science makes our holidays fun. And it's our way to use the topics of science and engineering to help celebrate the holiday season with you and your families. I'd like to start with one or two announcements. The program will last an hour, perhaps a little less, perhaps a little more. It is being recorded. Closed captioning is available. And for those of you watching, you'll see that American Sign Language interpreters are available. Their names are Steve and Tiffany. Everyone in this webinar is muted. However, we would be very pleased with comments and questions or little ahs and oohs that you put in the Q&A part of the Zoom webinar. Chat has been disabled for today. Our goal is to have fun, to learn something, and to enjoy science. And so I'd also like to say a happy holiday season to everyone, and I hope you're ready for hopefully an enjoyable presentation. We sent out a few instructions if you'd like to do some demonstrations along the way with us. There are 4 different elements here that if you have them or close by, we'll use them during the coming set of discussions. Okay, so this was a real team effort. I'm a professor of mechanical and aerospace engineering at Princeton University, and our team comes from Harvard University and Princeton University, and is a talented set of scientists and engineers who made all this possible. And you'll be meeting them during the next hour. We thought it would be useful to ask, where is everyone from who's on this webinar? So we made a little map of the world to see where people are joining us from. And the stars on this map indicate where people are joining us from. And in fact, people watching, you're from all over the world. And so we're really happy to have you with us and happy to have you learn and talk with us about some of these subjects. What's our main goal? Our main goal in this kind of activity is to convince you, the children, the parents, the families, that the world is an amazing place. And we're going to try to show you some ideas you may have never seen before, and maybe some ideas you never thought about before. We're going to do it with some videos. We're going to do it with some demonstrations. We're going to do it with some images. The spirit of this is how scientists and engineers think about the world. And we will be doing a few demonstrations in the laboratory, and hopefully you'll be joining us with a few demonstrations of your own at home to help us. If we were live, we'd be together in a room and we'd be interacting with you that way. And so we're trying to make the most of this virtual presentation to mimic that. Now, there's no better way to begin than with a quote from perhaps one of the great scientists of all time, Albert Einstein, who said, "In the matter of science, the first lessons should contain nothing but which is experimental and interesting to see." Now you can see on the screen that Albert Einstein was a very serious man, but he had a fun side. He had a fun side where he enjoyed that. And in fact, in Princeton, there's an ice cream parlor where he enjoyed getting ice cream. So hopefully that's something that many of us also enjoy. Today's theme is materials. So our first goal is to ask you and get you to think about, what are materials? And to a first approximation, everything we come in contact is a material. So for example, the food we eat, here the picture of spaghetti or the sauce are materials. Some of these materials might be like the food, soft and chewy. On the other hand, there's the plate on the table, and the plate and the table you might describe as hard. They're breakable, as you probably know, and they break very sharply. And the word we use to describe that is brittle. So everything around us is a material. We are materials. The computer screen you're looking at is a material. When you woke up this morning and hopefully brushed your teeth using toothpaste, that's a material. And the soap you used is a material. And for those of you fortunate enough to have your hair, the hair gel you use is a material. So materials are everywhere around us. And we asked you to share with us some words that you think about when you think about materials. And here's our word cloud of the words that you shared with us. And maybe you can look at that and maybe find one of the words you sent in. That would be really wonderful. But if you see my cursor, you'll see that some of these words we're going to use today in describing materials and how they're used. We encourage many of you to send us images of you and material. And so here's a little collage we put together with the images you sent in. And some of you, maybe you can find yourself here on the screen. And some of the words that we or you used when you sent this in. Okay, so we want to play the role of the scientist or the engineer. We want to investigate materials and how they, what characteristics they have, what features they have, and a scientist would say what properties they have. So we're going to look at materials today that break easily, and we'll refer to that as brittle. Some of them are soft and squeezy or squishy. Some of them are very hard, like the table I'm in front of me. And there are other properties we'll talk about. We'll look at how materials respond to changes, whether that change is a temperature change if you make it hot or cold, whether you try and flex the material or bend the material, whether you bounce the material. We'll look at some of these together. And all of these things together help us understand how materials are helpful to us, and to the scientist, how they're fascinating in their own right. Now, many of you are sharing gifts this time of year. If you happen to have a Christmas tree at home, you know that around the tree are materials. The tree itself is a material. The cardboard of a box is a material. The paper that wraps it is a material. And if you look under some trees, you might find even dog bones. And so some of our favorite friends wish everyone a happy holidays. Okay, so materials are everywhere. And if you're a scientist and you want to begin studying them, you need some basic ideas. And some of those the children watching this have learned in school, and you will recognize this little map. This map, I've given the name of it here. You learn about it in school. You can tell your parents right now who you're with about this. This is called the periodic table, and it lists all the elements known to humanity. So we have a quiz for the kids. We're now going to see how well you learn this in school. So let's ask, and maybe you can tell your parents, what is He? Now I can't hear you, but maybe you're telling your parents, well, He stands for helium. Okay, so now we can try another one. C, what does C stand for? C stands for carbon. And H stands for Harvard. No, I'm sorry. H stands for hydrogen. Many of you might have been telling your parents that. So we can do another one. Next is N. N stands for nitrogen. Very important element. P stands for Princeton. No, that's I just happen to live there. P stands for phosphorus, and O stands for oxygen. So you can talk about this with your family. And we're going to see these atoms, these elements appear during today's talk in different places. Now, the individual atoms, which we've already seen, they're what you often call the building blocks of nature, the building blocks of everything we use in life, the building blocks of materials. And when you put atoms together, you get molecules. The smaller ones are easy to recognize, so we'll call them simple molecules. And here we see hydrogen, which is normally present as a gas, and oxygen, O2, present as a gas. And you might want to tell your parents that you recognize CO2, carbon dioxide, which is very important in the world. And of course, there's water, H2O, another common molecule. And when you organize many of these materials in together, you sometimes organize them in a regular way. And so if you did that, you might have learned that some of these materials would then be called a crystal. And you see this every day at lunch or breakfast or dinner. Table salt, ordinary table salt, sodium chloride, NaCl, so is a crystalline solid. Okay, with that, I'm now going to turn things over to my colleague, Catherine Haller, who's going to tell us about some properties of materials. Catherine.
Hi, everyone. I'm so happy to, well, not see you guys today, but to be able to talk to you about science, which I love. It's getting pretty cold here now in New England. So I'm going to talk a little bit about materials that transfer heat. So I collected some things at my house. I have a cutting board that's made out of wood and plastic composite. You'll learn about that more later. And I have a metal measuring cup. So I'm going to ask you guys, if you have that with you now, was a plastic or a metal surface, if you can just reach out and touch each one like I did in the video to see which one feels colder. And then we're going to do a little Zoom poll where you can answer which one feels colder, the metal or the plastic or the wood feel colder? Or do they feel the same? And I'll just wait to see people are voting on the poll. It's pretty one-sided right now. Okay, we're going to stop the poll in a minute or two. Oh, people are still voting. Okay, so let's pause the poll now and we'll share the results. And so you guys can all see, most of you felt that the metal that you touched felt colder. Some of you felt like they felt the same, and some people felt that the plastic feels colder. So we're gonna move on to the next slide. And this is, we did this experiment at home. I'm gonna close the poll. And just remember which one felt cold to you, the metal. The metal felt colder than most of you. So we're gonna place the ice cube on each surface. But before we do that, we have a thought question. On which surface do you think that the ice will melt faster? And so we have another poll for you guys to vote on. And we'll let you guys keep voting. And I'm watching the poll right now. The results are different. So thinking about this, which surface will melt the ice faster? And I'm going to let you guys people keep still voting. And I think I'm going to, as you guys are voting, maybe we can move to the next slide. We're going to do the experiment. And we did this at my house, and it takes a while because our house is 74 degrees, as you can see on the thermometer there. If my husband had his way, it would be 90, and this experiment would have gone much faster, but we compromised. And so you can see, I'm going to end the poll now so that people can't cheat. We had sort of around 50% said the metal surface will melt the ice faster, or the plastic. So some people weren't sure. So you see in the video here, what do you see? You saw there was a lot more water around the ice cube on the metal cup. And then when I poured it out, you could see a lot more, and the ice cube was a lot smaller. So the metal actually melted the ice faster. So if we can go to the next slide, we have a little explanation for that. Um, um, so the ice cube needs to pull energy from its surroundings in order to melt, to heat up. Plastic is not very good at transferring heat energy, but metal is very good at transferring heat energy, which is why we use metal pots when we're cooking. But why did the metal feel colder? Now, if you take your thermometer or your temperature probe and you measure the temperature of each surface, the plastic and the metal, they're actually the same temperature. The metal feels colder because it's drawing heat from your fingers and you sense that as being cold. So that is a really interesting and useful property of materials, and one that I think is really fascinating. And as a chemical engineer, I studied that when I was in college. All right, I'm going to pass it back to Howard.
Thank you, Catherine. That was really wonderful. And I hope everyone enjoyed that. So we have another demonstration for you to help us think about properties of materials. This is a property we're going to refer to as a brittle material. We're going to break something, and we're going to use spaghetti. So I have in front of me some dry, uncooked spaghetti. So if you had prepared that, we'll start with that. I don't want you to do anything with it yet, but here's the thing we want you to think about. We want to bend and break the spaghetti. We'll do that in the next slide. And we're going to try to understand how many pieces the spaghetti breaks into. Okay, so we're going to have a few families come on the screen and do this with us. They're going to be part of our panel for the next few minutes, and everyone else can follow along at home. Okay, and when you follow along at home, we're going to, we need a little time, so we're going to launch a quick poll to just ask you a fun question. What's your favorite kind of pasta? And when you answer that, then we'll show Sarah will help us by showing the answer to the poll when it's ready. There's no real rush. We'll get some families on screen, and then we're going to all do an experiment together. All right, Sarah, you all ready with the launching the poll? Let's see what people like when it comes to pasta. And looks like there's a tie between macaroni and cheese and spaghetti and meatballs. Great. All right. And there are even other things people liked. All right. Excellent. All right. So now we go on, and now we're going to do an experiment together. So here's what I want everyone to do. We're going to take a piece of spaghetti. I want you to slowly bend it until it breaks. And I'm going to, and I want you to count the number of pieces it breaks into. And then we're going to do a poll. Now I'm going to stop sharing for a second so that you can see all the families that we've had join our panel do this together. So we want to bend the spaghetti and break it, and then pick up the number of pieces it broke into. And then I brought several pieces of spaghetti, and you can do this several times. And then you make a mess in your living room or your kitchen, and you then have to answer the poll question. How many pieces did your piece of spaghetti break into? And you should see a poll now on the screen, and you have to vote. And let's see. So, oh, I see a whole bunch of people joined us. Did you enjoy that? You can wave if you enjoyed breaking spaghetti for people all around the world. Yeah, what a great thing. Okay, so let's see if I can do this again. I'm going to go back and share the screen, and we'll go back to the talk. Share the screen. Guess it's this one. Okay, so we had the families join us. We answered the poll question, and now we can see what the answer to the poll was. So for some people, it broke only into 2 pieces. That must have been extremely brittle spaghetti. For about the same number of people, it broke into 3. Small number of people, it broke into 4 pieces. for 15% of you, the pieces went to everywhere. That's great. And so you're not sure what the answer was. Okay, so you can get a variety of answers, but the answers are typically the numbers you saw, 2, 3, 4. These are the kind of numbers. And in order to understand this, we're going to take a special camera called a high-speed camera, and we're going to look at it in the lab. And it turns out scientists, if you go into research as a field or go into science, often you have friends who work in different parts of the world. And here's a video from 2 researchers in Paris. And as it breaks, you see it breaks into, in this case, 3 pieces. Okay, and we can play it again so you see that. They set up an experiment so they could look at this extremely closely. And there you see how the middle is a small piece, but it broke on either side of it. And we also did this with an even higher speed camera. And so now we're going to play it again and watch a movie actually taken in the United States, that when it breaks, you see how it breaks first in one place, then in another place. And again, you end up with 3 pieces. So it's very common when you break spaghetti to end up with 3 pieces, 2 big ones and a little one. And you've now done this at home, and you've sort of seen some slow motion video to help you understand how brittle materials, at least when they're long and slender, might break. Okay, so that was our second experiment. And now we're going to turn to some of the things that come up when you use materials in sports. So I should ask, how many of you enjoy sports? I bet a lot of you enjoy sports, and lots of sports use balls. Balls often are, some are hard and some are softer. And here's a cool thing about them. When you kick them, for example, if it's like a football or a soccer ball, when you kick them, you can see if you get a special kind of imaging, a special kind of camera that can capture the instant of contact between the foot and the ball. You see the ball can deform because it's softer than the foot. And this kind of imaging actually was pioneered by a man named Harold Edgerton, who worked at MIT starting in the 1930s. And in fact, it really doesn't matter. Even if you take a hard ball like a golf ball and hit it with a metal golf club, you can see that on contact, the ball changes shape. We would say it's deformed. It changes shape in contact. Okay, so we need a little help to think about what we're going to do. So we called on Mickey Mouse, and Mickey Mouse is now going to tell us a little about bouncing balls.
Big Ben has won the spin and will serve first. And there's the service. It's a high parabola over the net and an easy return. And a tremendous backhand and a lob, smashing, slashing, crashing little game. Well, there's the first game to Little Joe. Oh, punch!
So to tell us more about materials and how they might bounce, I'm going to turn this over to my colleague, Dr. Janine Nunes.
Thank you, Howard. So I'm Janine, and after that very interesting tennis match, we're going to think about bouncing balls, okay? And what I want to think about, we talked about temperature earlier, is, well, how does the ball bounce when it's very cold? And so we're going to do another Zoom poll, right? And so which one do you think is true? Does the cold ball bounce less than a warm one? Does it bounce higher than a warm one? Or are you not sure? So tell me what you think. And then I'm going to do it in the lab for you. All right. So let's see what people think about a cold ball bouncing. So a cold ball will bounce less than a warm one. That's what most people think. Some people think it may bounce higher, and some people are not sure. Well, so we need to do this, and we need to do an experiment and see it in the lab. And so that's me in the lab. I bounced the ball, and you saw that I caught it. Howard talked about the high-speed camera, and so you can look, slow it down, and you see that the ball deformed. Now I take a really, really, really cold ball, and I'm going to bounce that ball as well. But Yeah? And then that you didn't see it bounce as high. And if you look really closely, you see that compared to the previous one, it also doesn't change shape. So the ball at room temperature, it deforms, it's flexible, right? And so when it changes shape and it comes back, it's elastic. But the core ball didn't deform, it stayed the same shape. It's more rigid or less flexible, right? And this is something you can try at home as well. You know, if you have a bouncy ball, you can put it in the freezer and then try to bounce it and see if it bounces as high. Okay, but I had another question. So what if I use more force, right? So I went back in the lab and I used a hammer. So let's see what happens if I hit the ball with the hammer. Okay, it bounced away, but let's slow it down and look really closely. Wow, you see how much it deforms when I hit it with the hammer? It's very elastic and it came back to its original shape. And that's a really, really cold ball now. And I hit it with a hammer and I smashed it. Now let's look closely. See what happens. Wow, you see that it broke into many pieces in the same way that the spaghetti broke earlier when you did that experiment. So it's showing you that temperature actually changes the properties of the material. You can go from something that's really flexible, but if you cool it down enough, it has a different property. It's now very rigid. And so I hope you thought that was interesting and you should try that. Well, maybe not the one with the hammer, but try bouncing the ball at home. So we're going to learn about other material properties. And so I'm going to pass it on to my colleague, Dr. Kanani Bey.
Thanks, Janine. So my name is Kanani Bey. I'm a postdoc at Princeton, and today I'm going to talk to you about where you just saw a rubber ball break. We're going to talk about how paper clips, which we reuse all the time to clip our papers together or to clean out different surfaces, they have their limits in how we can make them break. So everyone should have a paper clip at home. If you don't, that's okay. We also have a video that will show. So when you bend your paper clip, unfold it. It's hard, you can play the video, and then bend it back and forth. Does it feel different? Tell your parent. Does it feel like it's getting harder to bend or easier to bend? If we go to the next slide, we can think of bending as these little molecules or these balls on the right-hand side, which this is a model. So we as scientists use models to understand what's happening. And we can think of bending as shaking those little molecules. And you can see that those as crystals, as Howard mentioned, are metals, they can move around. And then we'll get this failure. But you'll see that it got harder and harder to bend. So what's happening? If we go to the next slide, we can think of the metal as a perfect crystal where these atoms are aligned perfectly. But as we bend it, we introduce a defect. And this defect is what we call a dislocation as material scientists, which leads to and more as we bend, leads to work hardening, which is what we call it when it gets harder and harder to bend, and it moves to the edge and more defects form and leads to the failure of these paper clips. And so these are really important to understand how metals break and how they can undergo cycling for different applications. So a material scientist will go into the lab and cycle their materials to see how they break. And so with that, all this work hardening made me very hungry. So we're going to talk about cakes, and my colleague Nikki will take over and tell you a little bit more about cakes and structure.
Interpreter switch.
Thank you so much, Kanani. Hi, everyone. My name is Nikki, and I'm going to tell you about material properties of cakes. Don't we all love a spongy, fluffy cake? Let's see what it is about these cakes that give them these textures. So if we take a slice of cake, like the one you see on the slide, and if we zoom in, we see all these air bubbles inside. And I'm going to convince you in the next few minutes that these air bubbles, these structures, are the ones responsible for giving the cake this fluffy, springy texture. So in order to see where these air bubbles come from, we have to look at the ingredients that go into making the cake. So we have flour, butter, sugar, vanilla. If you like chocolate cake, you can throw that chocolate cake in. But one of the most important ingredients in the cake, in this case, is the baking powder, which is a mixture of sodium bicarb and a weak acid, and these two would react in the batter, producing carbon dioxide, which is one of the simple molecules that we just learned about. And once you put that batter in the oven, these CO2 air bubbles would essentially rise, making the cake rise up in the oven, giving it that springy texture. Now we're going to do an experiment. What we're going to do is we're going to put the cake batter in the vacuum and see what happens. Now, before we play the video for you, think about it. The pressure in the vacuum is really, really low. Do you think the batter is going to rise? Or no, it's going to shrink in size? Now, let's play the video and see what happens. So here we have a vanilla cake batter in the lab. So what I'm going to do is I have put it inside this vacuum chamber. The pressure inside is extremely low. So let's see what happens. There it's me in the lab. We're applying the vacuum. And with time, we see that the batter starts to rise. Isn't that cool? So what's happening in this case is that these air pockets are getting larger and larger in size as the pressure is small. Now, we're going to do another experiment. So we're going to make some cake in the lab. We have two different set of batters. On the right-hand side, you see a batter with all these air bubbles, and on the left, you see a batter without these air bubbles. We're going to pop them in the oven. We're going to bake them for the exact same duration of time and see how they're different. On the right-hand side, you see the cake with the air bubbles. It has risen so much compared to the one without the bubbles. Right? Now let's do another experiment to see how they're different in terms of their mechanical properties. So what we're going to do is we're going to apply the same amount of force per unit area, which in the world of material science, we call it stress. So we're going to apply the same stress on these two different cakes and see how they deform. You see the one with the air bubbles, it deforms much, much more, which is indicative of the fact that it's springy, soft, and fluffy, whereas the one without the air bubbles, it does not deform at all. So I hope the next time you have a slice of cake, you look into the structure and you think about how all these wonderful ingredients and the structures within the cake give it, you know, that cake magic after all. So I'm going to pass it on to my friend Nikita, who's going to tell you about mechanical properties of another yummy treat. Nikita?
Awesome, thanks, Nikki. So we've learned about some interesting hard or brittle materials, and we've also learned about some interesting and delicious soft materials. But now, what if you wanted to combine some of those properties by combining two different kinds of materials? Well, material scientists call this a composite. That's any time where we've combined two or more materials so that we can use their different desirable properties to get some better material in the end. And you've actually seen composites many times in your homes. They're used to make lots of sports equipment, for instance, tennis rackets. They're used in panels for roofing and walls. And you also might have seen them in a sweet treat you might be eating in the holidays, s'mores. So if you think about before we do that, we want to know what your favorite part of a s'more is. So everyone, take your time answering this poll. It's a very important question. All right, so everyone wrap up answering your polls so we can get the results. And then we can learn a little bit about your favorite materials that are used to make these s'mores. Okay, so kind of an even split between chocolate, marshmallow, and all of it, which I would say is the correct 3 answers. All right, so now we're gonna see how these different materials in the s'more affect the properties of it. So what I'm doing here is I'm balancing some weight off the string that you see in the middle of the graham cracker marshmallow in the s'more. And I want you to first look at that first video with the graham cracker. So the graham cracker is holding the most weight, but you see the way it breaks really suddenly and it flies everywhere and it just cracks in 2. Now if we look at the marshmallow holds much less weight, but notice how it deforms, it squishes down and stretches as it breaks, and it breaks really slowly. So the marshmallow is a soft material. Now, if we take these 2 materials and we stack them into a s'more, you'll see that the s'more breaks slowly like the marshmallow because first it compresses and deforms because of that squishy marshmallow inside. However, the s'more can hold a lot more weight than the marshmallow because it has the layers from the strong graham cracker on the outside. So this kind of structure combines the strength of the graham cracker with the softness and flexibility of the marshmallow to make a better or at least different material in the end. So this is called a 3-point bending test, and engineers actually use this in the lab to determine different properties of materials, but you can also do it in your house. All you need is an adult to help you, some kind of table where you can prop up the material, and then something you can hang the weight off of. I use beams, so you can use any kind of weight you have in your house. And you can take some different materials and you can ask which one is the strongest, which materials deform or change shape as they break, and how do they behave differently if we stack them into a composite. And it's interesting to understand composites because they're very common in your life, and in particular, the kind of structure that you just saw with the spongy cake or the s'more are structures similar to what you might use every day. So if you think, for instance, about the helmet you use to ride your bike, it has a hard shell that's strong and also a soft and squishy layer of foam on the inside that deforms so that it can absorb impact if you were to hit your head on something. So this is really similar to the structure that we just showed you with the s'more. That said, you probably wouldn't want to make a bicycle helmet out of graham crackers and marshmallows, and engineers are using even cooler materials to make these interesting applications. With that, I'll send it back to you, Howard.
Thank you, Nikita. So now we're going to take a little bit of a change, and we're going to tell you about another kind of very common material, materials that come up whenever you handle plastics and other kinds of similar objects. And the molecules and behind them are called polymers, which I've highlighted on the screen. So the plastic bottles you use to drink water or beverages out of, or the shopping bags you use, are made out of a kind of material called a polymer. The wood of a tree has a polymer in it that's called cellulose. So every time you look outside and see a tree, you're seeing a large amount of a polymer. And the web made by a spider is another kind of polymer. So polymers come in many kinds of applications and many kinds of things in our everyday life. Now, what is a polymer exactly? Well, a polymer is a long molecule, a very long molecule that has many parts that repeat over and over again. Now, I showed you earlier, we introduced oxygen and carbon and hydrogen, which I'm pointing to, and chemists have different ways to draw that. Sometimes they label them with colors, and sometimes they label them with this black bar diagram. And this black bar diagram, wherever the black lines intersect, is also a carbon atom, which we'll see later. And on this diagram down below, we've shown you this long molecule, and I've tried to highlight, so if you take one part of it, which I've highlighted in the box, you'll see now that it's repeated to its left continuously. So these continual segments of a molecule lead to what are called polymers. Sometimes a chemist will call it a big molecule or a macro molecule. And why this word? Well, poly, as you probably are aware of, means many, and mer in Greek means part. So a polymer is a molecule with many parts, and usually the parts are simply repeated. So if you can picture in your mind a little bit of a molecule, this a chemist or a biologist would call an organic molecule. It's made mostly of carbon and hydrogen, and you try to make it longer and longer and longer and longer still, you'd have a long molecule, and you'd call that a polymer. Now, to show you how you can make a very common kind of polymer, I'm now going to turn this over to my colleague in chemistry, Nicholas Garcia.
Thanks, Howard. Hi, all. My name's Nick. And now that you've heard a little bit about polymers, I'm going to tell y'all a little bit about nylon. So nylon is a name for a specific group of synthetic polymers known as polyamides. They find use in many everyday items like fabrics for clothing or parachutes, or in plastics like zip ties and toothbrush bristles. Shown below is an example of a particular nylon called nylon 6,6. It's called nylon 6,6 because each carbon chain has 6 carbon atoms. That's sort of the the naming convention that we use. Each little kink in this line drawing represents a carbon atom. So how is nylon made? Well, there are a few different ways to make different nylons, but I'm going to show one way to make nylon using some very simple chemistry. If we combine 1,6-hexane diamine, which has 6 carbon atoms in its chain, and sebacoyl chloride, which has 10 carbon atoms in its chain, we can make nylon 610, which is actually the nylon used in the bristles of a toothbrush. So I'm going to show you how one would do this in the lab. So here I am in the lab with 2 beakers, one with 1,6-hexane diamine and water on the right, and one with sebacoyl chloride and hexanes on the left. Hexanes is a greasy solvent we use that is sort of like oil. And if you've ever added oil to water, you'll know that they don't mix. So as I slowly add the sebacoyl chloride solution to the beaker, it stays on top above the water, and the 2 reagents begin to react where the hexanes and water layers meet, making a very thin film of nylon. So here I'm done adding the solution, and I'm going to try to grab that film of nylon. As an aside, you'll notice I'm in full protective gear, which is incredibly important when working with dangerous chemicals. The chemicals I'm using are both corrosive. So I want to cover myself in case of any spills. So yeah, this is actually not as trivial as it sounds. Okay, there we go. So after I successfully grab the nylon, I carefully pull it up out of the solution. I don't want it touching the sides of the beaker because then I won't get that nice strand of nylon. And then as I finally get it onto this metal rod, I can start pulling out more nylon. And as I'm rolling up this rod, I'm taking the nylon out of solution, allowing more nylon to be made at that interface. And so this is after what it looks like after a minute. This is after 2 minutes of rolling. Then 4 minutes. I did not realize I would be making this much nylon at the time. It took almost a full 8 minutes of rolling up nylon before the reagents in the solution were all used up. You can see the strand is a little thin here. But it's pretty cool. You know, I took 2 simple organic compounds, followed this procedure, and in the span of about half an hour, I got a fairly sizable amount of nylon. Yeah. Anyways, back to you, Howard.
Thank you, Nick. That was really wonderful. Okay, so we just want to see how you're all doing. So we need to take a little poll to set up the next part of our program. How many of you brushed your teeth this morning? And let's try to honestly, and we'll see, you know, you don't have to tell your parents one way or the other, but there's the poll. Did you or didn't you brush your teeth this morning? And you'll see your teeth and toothpaste on the slide, and they're part of the next part of our show. And now we'll get an idea from all around the US and all around the world, how many of the young people brush their teeth this morning? And maybe the parents could have answered too. All right, we'll launch the poll when we get it. And it looks like 70-30. So 70% said, yes, they brushed their teeth. And 30% still said they had some more stuck in their teeth and they didn't brush their teeth this morning. Excellent. Okay, so why are we thinking about this? Well, sometimes polymers are not just sort of the structural materials around us, but they might be living materials. And to tell us a little about that, I'm going to turn it over to my colleague, Professor Bonnie Bassler.
Okay, well, thanks, Howard. And I am delighted to be here. And we've learned about so many fascinating materials today, and the materials are all around us. And what I want to tell you, which Howard just gave you a hint about, is that sometimes materials are living and they actually make themselves. And so the reason we showed you your teeth is because there's a living material on your teeth that you experience, and 30% of you all day, every day, but some of you every morning. And so these are materials that are made by living cells called bacteria. And so on this first left-hand part of the slide that Howard's showing you is that these films, these materials that bacteria make, are on every surface on Earth. They're usually invisible to us, but they are there and they are materials. And so just to give you a few examples, in Yellowstone National Park, these beautiful gem-colored geysers, those are bacterial mats of biofilms that give those pools those beautiful colors. In your gut, you have bacterial biofilms in your intestines, and they help you digest your food and they keep you healthy. And then there'll be a couple more. Some that you may have also encountered are in pipes. Sometimes pipes get clogged. That's because bacteria in films, they make films, they stick to surfaces of pipes, and they grow and grow and grow and make more and more and more of this living material until the entire pipe can get clogged. And then the one that we did the poll about are your teeth. So you guys know that every morning you wake up and your teeth are covered with this gudgy, sort of squishy, gross film. Well, that is a community of bacteria, a biofilm that grows on your teeth every morning. 60% of you seem to brush that off, but then it comes back the next day. And that's because these bacteria live in your mouth, and they're actually a fantastic community that lives on your teeth and in your mouth. And so in the picture Howard's showing you on the bottom right, that's a picture on your teeth, and each one of those colors is a different species of bacteria that all live together in this community that form that film that you feel on your teeth each morning. So the world is covered in these living, invisible films of bacteria. And so the way bacteria make biofilms is shown in this next slide. So they swim around. That's the movie. You're looking under a microscope. That's a movie of bacteria zipping around. They swim, but then if they encounter a surface, so your teeth, a pipe, the ground, a rock in a river, they attach to the surface and they start to grow. But so that's a hard material, the cells, like the balls that you've heard about. But then on top of that material, the bacteria make a polymer, like Howard told you about. They make a polymer of repeated units, and that polymer makes another material, a soft material around the bacteria that makes like a suit of armor for the bacteria to live in. And then together, if you go all the way to the right of this film, the bacteria grow and grow and grow, and that film around the bacteria, the polymer, grows and grows. And so that's how they form these films that can ultimately be on your teeth or even corrode a pipe. So it's hard materials, the cells, inside a soft material, the polymer, but both of those materials are living and they make themselves through biology. Okay, on the next slide, Howard's going to show you an actual biofilm being formed. The yellow dot in the middle, this is under a microscope, that's a cell, and it divides, and it makes all these daughters and sons until they all grow together, they line up like little soldiers, and what you can see is that each of those pinpoints is a cell that came from the original founder cell, and that's a bacterial biofilm that formed in real time. There it is again, because it's fantastic, under the microscope, right? And so this is what happens on your teeth or happens on all of these surfaces. And so biofilms, so now you're looking again at a picture of a mature biofilm. In the middle in the gray, that's this beautiful structure. It's like an architected community. So that's a biofilm. And what's amazing and terrible about bacterial biofilms is because they form these materials that are very resilient, they're very hard to get rid of these films. So they resist antibiotics, so medicines, they can resist changes in pH, they can resist flow. So like in a pipe, they get all clogged up, they stick there, they can resist salt shock. And so on the one hand, bacterial biofilms are really bad because they can cause infection and they're hard to get rid of. They can cause damages to all kinds of surfaces that we need in our lives or in industry. But on the other hand, biofilms are really fascinating because they are living, growing materials, like we've been learning about today, with all these fascinating properties. And so scientists want to learn about biofilms because if we could understand how these living materials get formed, perhaps we could harness that understanding to make inventions and make products that we need for humanity. So thanks for letting me tell you a little about living materials.
Thank you, Bonnie. We're have a few little pieces left in our show, so I want to begin to tell you a little about how water comes up and is used with polymers. Who's that? Oh, Is it Santa? Is Santa here?
Well, you didn't have anybody from the North Pole. I had to come.
Well, Santa, how about if you tell us about polymers and water?
My favorite. I have to say, we say ho, 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 but we also say H2O, 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 because snow is made out of H2O. Just remember that, kids. So I had to join you because, as you may know, there's a very famous poem book about me, and one of the lines in there is, he had a broad face and a little round belly that shook when he laughed like a bowl full of jelly. Well, jelly is made out of polymers, and it's made out of a particular polymer that can trap a lot of water. And this class of polymers form these structures called gels. And I'm just going to show you a few that you might know of. If there's some parents here who have little kids, you might have used diapers that really absorb some of the byproducts that those babies produce. If you have ever watched Elf, the movie, they use fake snow, which is actually a polymer that absorbs a lot of water. And if you're like me, you like dessert a lot. My belly may just be made out of jelly. I don't know. But I really like Jell-O. So I'm going to tell you a little bit about Jell-O because it's got a polymer in it. And Jell-O is actually called gelatin, and the polymer in it is cellulose. So when you have dried Jell-O out of the packet, it's got all these long molecules that Howard talked about, and they're stuck together with cross links. There's little green lines there. But if you heat it and add hot water, you add the water and those molecules kind of separate and move around. But when you cool it back down with the water in it, the cross links form again, and it binds it together and traps the water inside. So like I said, these polymers get tangled together, they get attached to each other, and they trap a lot of water. And I made a little video with my elves where I made some Jell-O that had half the water. That's my 2X gelatin. And then I made one with the recipe on the box, which is the right amount of water. And then I made some with twice as much water, and that's just kind of a mess. But still, you can see that even though we have added more water, it still makes a gel and holds together. So I'm going to just show you some fun things that we like to do at the North Pole when this season is over. We like to make the Jell-O and do some slow motion photography of it with our phones. But I hear that one of the scientists on this call here, she can do it in the lab even better. So I think we got to show her on the next slide. Thank you, Howard. And everybody have a very happy holiday season.
Thank you, Santa. And Santa, stay on the line because here Janine is in the lab showing what happens when a piece of Jell-O hits the surface and you watch it change shape so suddenly.
Yep,
And you
Janine is
show that to
always,
your elves, Santa.
Janine is always on the nice list. Good
Oh,
job,
yes.
Janine. And good job, Howard.
Thanks, Santa.
Happy holidays, everybody.
Okay, well, we're nearing the end of our show, so I just want to remind you of a few things, and then we have one other little treat for you. Our program was about materials and the science of materials, which is called often material science. Materials are everywhere around us, and we often select them because of the different properties that we've tried to tell you about today, whether they're solid-like materials or polymeric materials or composite materials, and they can be rigid materials or soft and flexible materials, many different properties of materials. And we saw that in many of the examples we got to talk about with you today. And so that reminds us that materials make our lives merry, not only every day, but also at the holidays. So with that in spirit, we have one little extra treat for you, which Daniel Rosenberg is going to share with us. Daniel.
Thank you, Howard. Okay, well, it's time to do a little bit of lecture demonstration. And for this holiday lecture, I decided to make a holiday light. And I started out thinking about colors of materials. And one of the properties of the material, of any material, is its color. And most materials reflect light, and the color of the material comes from the light it reflects. And that's how paint and ink works. But some materials actually give off light. So the glow in the dark stars that you have on your bedroom ceiling, or an LED, those materials are actually giving off light. And a flame in a fireplace or in a little beaker with some alcohol, the flame is giving off light, and we can use different atoms of materials because each kind of atom emits a certain characteristic color. And so for this demonstration, I used boric acid in methanol, which is a kind of alcohol fuel, and boric acid in methanol gives a green flame. And then in another little batch of methanol, I added lithium chloride, and that makes a red flame. Methanol itself, when it burns almost invisibly with a very pale blue flame. So that's good because it allows those colors to pop out. So the kind of light I decided to make is a flame tornado. And hot flame, when fuel burns, it's hot and the hot air rises. And when the air coming in from the side is spinning, it spins faster and faster as it gets closer to the center where the air is rising. So it makes a tornado. And so here's a little GIF of one in the wild. And now here's the flame tornado, a holiday flame tornado in the lab. So I give it a little spin, and the screen itself is acting to spin the air. So as the air comes in from the sides, the moving screen gives a little push, and as it gets closer to the center, it goes faster and faster in a little whirl and turns into a tornado.
Thank you, Daniel. That was a wonderful way to bring our set of presentations to close. So let me just end now with a few remarks. The idea for this kind of lecture, where we try to share science and engineering themes using demonstrations, some of which you help us with, goes back at least to Michael Faraday, a great scientist in England in the 19th century. And we took the spirit of many of the things that he did in holiday lectures, Christmas lectures for children, and we've embedded them over the years in the style of program that we shared with you today. As I told you at the beginning, many people were involved in putting this together, and I can't thank them enough, but reading from left to right, Nick Garcia and Konani Bay and Nikki Abassi all helped. You heard also from Catherine Holler and Nikita Dutta. Sarah Wenzel helped us in many ways, as did Ryan Signora. Dan Steinberg heads many of the outreach efforts at Princeton. You heard from Janine Nunes, Daniel Rosenberg, and my colleague, Professor Bonnie Bassler. So this was a real team effort, and we need to thank all of them. Finally, we'll just close by saying thank you for joining us for this virtual version of a holiday science lecture. There are many programs at our universities that we thank. We're going to hang around and answer questions. We can also, once we turn off the recording, we're happy to go online with you and answer questions and talk with you. But please accept my best wishes on behalf of all my colleagues to wish you a wonderful and safe and healthy holiday season. So thank you again. If you'd like, we can use the chat to answer some questions. I think my colleague, Catherine